morning, friends and dear students. It gives me immense pleasure to be here for my course Flight Mechanics, which is basically a aircraft performance. We are dealing here with climb performance, and we have already done about glide performance. So in today's lecture we are going to discuss about glide performance. In this glide performance we will see sink rate, minimum sink rate and the glide ratio. These are the few topics which I am going to cover. I am Dr. Yagya Dutta Dwivedhi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. In today's lecture, I am going to take few topics like sink rate, minimum sink rate, glide ratio, best glide speed, effect of wind on best speed to glide ratio, typical value for design parameters. So this will be very useful. First, what is the glide and when we are sinking? So it is in the descent flight. If you see that I am at the cruise flight here, and as and when I require to come down, it has to nose down, it is descent, and all of a sudden engine is failed or power is reduced due to some reason, or for the practice also. For pilots to practice, if the engine is failed, pilot will switch off the engine. In that case, there will not be any thrust. So the flight which is not having any thrust, that flight is called the gliding flight. And in the gliding flight, it is very much essential that how much it is sinking, because it should not sink very fast, so that the pilot can find out the place where it can land safely. So that is the objective of the sinking rate. So this you can see here, this is the model of aircraft. Here we have the wing, this is the vertical tail, this is the horizontal tail. Here we have the controls, that is the elevator is here, ailerons are here, ailerons are here, elevators are here, rudders are here. Here we have the leading edge flaps. Here we have the at the root, at the near the fuselage we have the flaps. Flaps are the lift producing device, especially used for landing on takeoff situation. So here we are discussing about the descent flight where power is not there. If this is the situation, what will be the condition of the aircraft and what will be the descent rate of the aircraft? This we are going to discuss in today's lecture, which includes the sink rate, minimum sink rate, glide ratio, best glide ratio, effect of wind on best speed to glide ratio, and also a very important, the last topic, that is typical value of design parameters. It is very much essential for each and every aeronautical student to understand this. I will again focus that the last point is very, very important. Each and everyone, engineers, not only aeronautical, any engineer which is involved in the aircraft design, they must understand the last topic, the last typical value for design parameter, that we have to understand. So sink rate means per unit time how much it is coming down if the engine is failed, and we need a minimum sink rate so that more time it can be available for the pilot to see the place where it can land. And what is the best glide ratio? This also has to be understood. So I will go here with just I gave some introduction, and now I will go for the sink rate, and I will draw the diagram of the aircraft. Okay, this is the aircraft in normal, the velocity is v. This is the horizontal. In this case, I will draw with another color, that is the lift is perpendicular to the v, drag is in the same direction, and weight is always towards the earth. So this is the, and in this case, if you see, if I draw this v, there will be a horizontal and there will be a vertical velocity, and this will be the horizontal. This is called vh, and this is called vc. This is, if this is the gamma, here this is the gamma angle, vc is equal to v sine gamma, and this is called rate of climb. This we have already covered in our previous lectures. So as of now, we have seen with TA and the PA. If no power is, so if there is no power, there is no thrust available, or power available. So sometimes there is power failure, or sometimes pilot does it for practice, for emergency practice, and switching off the power plant. That is also another name is engine. So in this there is no thrust. We have seen in our previous lecture that rate of climb Vc, it is also called rate of climb, Vc is equal to Pa, that is power available minus power required divided by W. This we have seen. In case if engine failed, then what will happen? Pa is equal to 0. So Vc is equal to minus PR by W. And this negative point here, this negative climb rate is called sink rate. So this is the definition of the sink rate. So this sink rate here, this is the sink rate. This sink rate is the negative climb. That is the purpose of, means climb is always upward, but sink rate is always downward. Okay, so we will see that how this sink rate are. So this sink rate is also called negative of climb rate minus Vc, and it will be going down. Aircraft will not go up, it will go down. Here I have shown the upward, but in fact if T is not there, your aircraft will be coming down. So now we have to again see that we can write this sink rate as a Vs. So this Vs is equal to minus Vc. This we can write as a PR divided by W. So Vs is equal to P sub R divided by W. So this is the sink rate for zero flight condition. Now if we find out, we have to find power required, as we have already, as earlier derived, we have seen that PR, this PR is equal to CD naught L V cube rho divided by 2W by SW plus CD naught L into CL plus 2 into W by SW divided by pi E aspect ratio rho into V. So this into here we can write W. Now we have to find out the stall speed. Stall speed is denoted by Vs. This Vs is equal to CD naught L rho V cube divided by 2 W by SW plus CD naught V plus 2 W by SW divided by pi E aspect ratio rho into V. If we want to minimize, we have to differentiate with respect to velocity V. So here we know that Vs is equal to PR divided by W, and PR is the function of V, but W is weight, is not function of V. So we have to find out V minimum sink rate, V minimum sink rate. This V minimum sink rate, we can also write it as a V PR for minimum air speed. Minimum air speed. So we can write it here in this way, that V minimum speed is equal to, we have already find out in the last lecture, whole under root pi E aspect ratio CD naught L plus again under root 2 pi E aspect ratio CD naught L whole square plus 12 into pi E aspect ratio CD naught, here whole under root again W by SW divided by rho. So this is the equation for V minimum speed, and so we can write here that Vs is equal to PR by W. So Vs minimum, PR minimum divided by W, and we know that PR minimum, we have already calculated PR minimum. So we can write it here that this is equal to here we can write power required minimum, PR minimum is equal to approximated 4 under root 2 CD to the power 1 by 4 divided by 3 pi EAR to the power 3 by 4 W by SW divided by rho. So this is the PR minimum that we will see it. So we will get the VS minimum. VS minimum is equal to 4 under root 2 CD naught to the power 1 by 4 3 pi E aspect ratio to the power 3 by 4 under root W by SW divided by rho. So this is the equation for minimum speed. This is the equation for minimum speed. Now this takes, now this we have to maximize the endurance. If we fly with this VS minimum, the endurance will be maximum. It will stay long time in air. But if you want to find out the range, then we have to find glide ratio. So this we will discuss in the next slide. What is the glide ratio and what is its importance? So this velocity here, which we have find out here, Vs, is useful for the endurance. But if you want to find out how much distance it will cover, which is the best distance to find out the, then we have to see the glide ratio. So here we will discuss about next topic, which is the glide ratio. So if the power is failed, in form of range, how much range it will cover, and this range is depend upon the glide ratio. Glide ratio is a measure of, so what is the glide ratio? Glide ratio is the measure of range of aircraft once it loses the power / thrust. This ratio is depend upon the ground velocity. That we have to understand. The new term has come, ground velocity, and it is represented by Vg. In case there is a no wind condition, atmospheric is not producing any wind, Vg will be equal to the V. So if we glide ratio, we can define as glide ratio, it is Rg is equal to Vg by Vs. Vg is a ground velocity and Vs is a sink rate. So if I draw a diagram, I will just choose some another color here. This is the aircraft. From here, this is the horizontal, and here is the one velocity vector, which is it is sinking. Velocity is sinking down. Velocity is in the downwards direction. Weight will be always in this direction. Lift will be always perpendicular to this velocity vector. Lift. Drag will be in the same direction of the opposite of this in the same. And here we can see that this is the gamma. So if we make one V like this, so this is the sink rate Vs, this is the your velocity V, and this is the your Vh, and this is the gamma. So Vs is equal to V sine gamma, and it is in the negative direction. So if we take the free body diagram, then we can find out that L is equal to, and if you see here, it is not in the same direction, sorry. This will be, this is down like this, and this is like this, L. This is W, this is the W cos gamma, and this is the gamma. So if we resolve the forces as we have done earlier, seeing the free body diagram as shown here, we can see that the lift is equal to W cos of gamma, and this drag is equal to minus W sine of gamma. So just we will discuss here something about, because here angle is minus gamma, so we know that cos minus gamma is equal to cos gamma, sine minus gamma is equal to minus sine gamma. By the trigonometry, this is the relation. So we got here L is equal to W cos gamma, because cos minus gamma is equal to cos gamma. So L cos gamma, and this D is equal to, it has the sine gamma, so it is minus sine gamma. So we got this two equation here. Now with no wind condition, glide ratio is Rg naught, because no wind, at zero wind. So now I will change some other color. So we can write here Rg is equal to Rg naught at zero wind is equal to V cos gamma divided by minus V sine gamma. So Rg naught is equal to Vg divided by Vs. So this Vg is equal to Vh. Ground speed is equal to Vh. So this will write Vh divided by Vs, this horizontal, and this is the vertical. This horizontal we can write as a V cos gamma, and here it is a minus V sin gamma. So this VV is cancelled, minus cos gamma divided by sine of gamma. And we know that if you see here, cos gamma is equal to L by W minus sine gamma is equal to D by W. If you put this value, cos gamma L by W minus D by W. So this W is cancelled. So you will get L by W. So this very important result came. It is surprisingly that RG naught is also L by D. So L by D is RG naught, and we know very well about L by D. So we can write here that RG naught is equal to L by D, CL by CD. We can further write that CL divided by CD naught plus CD naught L into CL plus CL square divided by pi E aspect ratio. This we have already, you remember that we have already drawn this equation earlier. So here we can write that this CL, we can write that under root CD naught pi E aspect ratio, and this we can see that we can put in this equation, and this is also called under root CD naught by K. So now we will see that how we can, okay, go ahead. So this we can find out the L by D ratio maximum. So L by D max. So L by D max is equal to RG naught max. This is equal to under root pi E aspect ratio divided by 2 under root CD naught plus CD naught L under root pi E aspect ratio. So this is the maximum zero wind. This is the maximum zero wind glide ratio. Now we have to find out best glide air speed. So now we will work for the best glide speed, and we know that already that CL is equal to under root pi EAR CD naught. Also CL is equal to W by half rho V square SW. If gamma is very less, L is equal to weight for steady state flight. In this condition, we can find out that approximated under root 2 by under root CL under root W by SW divided by rho. So this is the speed, and the best glide speed is glide speed best glide speed. So best glide speed is VBG naught, that is a V at minimum drag, approximated under root 2 by 4 under root pi E aspect ratio CD naught under root W by SW divided by rho. So this is the equation for best glide speed. So if you know the aspect ratio, if you know the wing loading, if you know the density, you know the CD naught, you can find out best glide speed, and in this only pilot will have the minimum sink rate and it can fly very easily and attain its objective. So now I will go for the next topic, which is related to the same thing. If you see here, sink rate I have discussed here, the sink rate, this I have already discussed. Again I have put here in my own words here. Minimum sink rate, glide ratio, which I have just now I have covered up to here. Best glide speed is equal to VMD under root 2 by, it is root of 4 pi E aspect ratio CD naught W by SW. To have the maximum range, so we have to fly the aircraft at a minimum drag speed as given in the equation A above. Now we will see effect of wind on best speed to glide. This is my last topic of this lecture. So effect of wind on best speed of glide flight. First thing is the headwind and the tailwind. If the wind is headwind, then what will happen? And if it is the tailwind, of what will happen? This we are going to see here. So here we can see here the effect of wind on best speed of glide flight. Here we have the headwind here. So just you can see here, if it is a plus, it is a headwind. It is a minus, it is a tailwind. So if it is a headwind, this is the our headwind here, and this is the our power required. So it is increasing as it is from minus to plus velocity. The headwind, it is increasing, and if it is the other wind or tailwind, it is decreasing. Even the side wing, it is decreasing. So headwind is giving better efficiency, but if you want the range and all, tailwind is good. Now I am going to discuss about this glide ratio for wing loading and what is the effect of headwind and the tailwind. If area SW is fixed and varying, the weight W is called the wing load variation. Tailwind to help the glide ratio, and wind not favorable for the tailwind to help the glide ratio, and headwind, here it is a headwind not favorable for the glide. So if you see here, this is the, if it is the headwind is here and this is the tailwind, if it is a minus 50 meter per second or not, it is very nice, your glide ratio is 20, but if it is the headwind, the glide ratio will be less. So CL by CD will be less, and here CL by CD will be high. So this is the difference. And if it is a normal weight, and if you decrease the weight, as you decrease the weight, your slope will be increasing like this. It will come like this. So these effects of wind, headwind and the tailwind, playing a lot of role for the glide. If you want to glide the aircraft, you see, glide is only what is the meaning of headwind and what is the meaning of tailwind. So if you are flying like this and wind is flowing in opposite direction like this, then this is the headwind. And if your aircraft is flying like this and tail is from behind like this, it is a tailwind. Tailwind is not good. Tailwind is good for maximum CL by CD. Your range will be very high. So if you want to fly aircraft for more distance, if your engine is failure, if engine is not failure also, it is very good practice to fly your aircraft in a tailwind when you reach on the cruise. But during landing and the takeoff, headwind is very, very good, because that time we want more lift. More lift and the more drag for landing we required. In that time, we have to put down your flaps. So more lift coefficient will be increasing, velocity will be decreasing, drag will be increasing, your aircraft will be in a very good condition. So during landing and the takeoff, we want more lift coefficient. So that time the headwind is very good to lift the aircraft to counter the weight. But as and when you reach the maximum as the cruise flight, from where you have 90%, you have to travel the distance. There we need a fuel economy. We have to save the money. For that condition, we want that tail wind should be there. Tailwind is increasing the glide ratio, and in case engine is failed, that time pilot has to fly the aircraft in a tailwind. Try to fly in a tailwind, maximum distance it will cover. As and when he sees some place where it can land safely, there it will be landing. So here we have shown here that RG, that is the glide ratio of the aircraft, is depend upon the headwind and the tailwind. If you have the tailwind minus 50 knots, you can go up to 20 CL by CD. But if you have the 50, then it may be somewhere 4, 5, 6, as shown in the plot here. That we have to understand. So speed, wing loading and stall speed in glide. So here we will see that this I think we have already covered. Minimum power, airspeed, these things are already covered. So it is here under root 2 by pi E aspect ratio CD naught. So this minimum drag speed is a function of E, that is Oswald efficiency, aspect ratio, CD naught, wing loading, density and the CL max. So in the next slide, I am going to discuss about some very, very important. This slide I was telling before also, everyone should understand. Just you don't jump for design without understanding this slide. So here we have aspect ratio. A typical aspect ratio for aircraft is somewhere 8, 9, 10. But for the sailplane, it can go 19, 20, 18 like this. Typical aircraft will have 6 to 8. So if we design our aircraft for RC plane, ours should be somewhere 7, 8, 9 like this. Oswald efficiency is range from 0.7 to 0.95, but in the ideal case we should select 0.8. CD naught should be 0.01 to 0.1. Ideal case where we have to, in the real practice, we have to take 0.02 to 0.05. Wing loading 1 to 100. Need to manipulate wing loading to meet speed requirement. CL maximum 0.8 CL maximum to 5. In this 5 we have to use the flaps, slats, etc. And here we will have 1.2 to 1.5 is a typical range for the CL maximum. For your normal aircraft, 1.2 to 1.5 is sufficient. Okay, so in this we have the references. Aircraft Performance and Design by Anderson. International Edition, McGraw-Hill's first edition, 1999. Then ESL by ME, Aircraft Performance, Theory and Practice. AIA Education Series, AIA. Any questions, you are welcome to ask. My email is yddwivedhi@gmail.com. Please do like and subscribe, and do comment if you feel anywhere I did some mistake. Please correct me, inform me. I will change the video accordingly. This will help to all others. So do not hesitate. Thank you very much for the joining. Be tuned for my next topics. I will be going for the maneuvering flight. My next topic will be maneuvering flight. In that, I will be covering the turn, then climb, then pull up, pull down. These all maneuvers I will be covering. In that, lift to drag ratio, that is L by W, that is the N. N means it is load factor. G factor and all I will be covering. So thank you very much for the joining. Let's meet in the next session.
Like, share and subscribe. Hit the bell icon for more updates.